Hi, I'm Leandro Facchinetti, and let's write some code together, shall we? What we have on the menu today is something very exciting for me. I have been waiting for this day for a long time. We are going to implement the Fourier Transform in our JSFX library that allows you to develop better looking, easier to develop JSFX, which are real-time audio processors for REAPER. And the reason why I've been looking forward to this day is that I have never implemented the Fourier Transform, and I only have a cursory understanding of how to use FFTs, the fast Fourier Transform, but I do have a grasp on the theory behind the thing. And today what we are going to do is actually to implement the definitional version of this. So it's like not the FFT, it is not fast. In fact, it is meant to be relatively easier to understand and to get around to get across the concept behind a Fourier transform. And then the FFT, the fast version of that, is already implemented in JSFX. You can just call it. It's probably faster than anything we could write in the language itself because it's probably optimized using C++ or something. So what we are doing is not necessarily super useful from a developer's perspective, a developer using the library, but it's definitely something that is nice to understand and play around with and implement from scratch. That's what we are going to do. We are going to implement this. I don't know how to spell this. Hey, Bo, great to have you here. Okay, I know how to spell the thing now. Before you start, can you make an inclusion for a slew rate in the library? Pretty please. Okay. We'll get to that at some point. Right, noted. Now let's try to spell this word. It is a weird spelling for me. All right. So we are going to follow along this chapter of this book. The book is called Digital Signal Processing for Engineers, the Scientists and Engineers Guide to Digital Signal Processing. And it has a high-level explanation of what a discrete Fourier transform is. I recommend reading the whole book, especially this chapter. There are some chapters in the book that don't necessarily... It's a book about digital signal processing, so that applies to things like visualization in medicine and measuring tectonic plates and whatnot. But we are interested in audio, so there are some chapters that don't really apply all that much. Most of them do, however, and it is a very good book. Once you have like a vague understanding of what DSP is about, you can get around this book fairly straightforwardly. In any case, there is this chapter 8, about the discrete Fourier transform, and we are more or less going to follow along with what they have there, and we are going to try to implement. It's not too much code, but it's relatively difficult to understand everything that's going on. So let's follow along. And if you're reading the book, I recommend that you go to the PDF because I found that the HTML version sometimes is missing some formulas and some mathematical symbols, so it's just better to go with the PDF. And I think that all the fixes, there is here a section about mistakes in the book. I think that all the fixes have been applied to the PDF as well. So let's start with the basics. What is the point of a Fourier transform and how is this going to play out? So you have a signal coming in. And in this case, this signal is kind of weird because it starts at 0, then it jumps to the top and to the bottom. But never mind that, you have some signal coming in. And the purpose of a Fourier transform is to represent these dots, represents this signal in a different way. We are not going to convert the material itself. It's just a different way of seeing the material. It's still the same audio coming through, but it is going to be represented in the computer in a different way. And this is the so-called time domain representation, where you just sample over time and you take a measurement. And this is going to be the so-called frequency domain representation. In this domain, we are representing the signal losslessly. We are not losing any information in the process. In fact, you can come back from the right representation to the left one, from the frequency domain to the time domain. You can come back and you're going to get exactly where you started. But the purpose of representing things in the frequency domain is that for some tasks, it is more advantageous to be in the frequency domain. And in the frequency domain, you see the signal not over time, but you see what are the frequencies that are represented here in this signal. In other words, this is like an oscilloscope. So I guess I can come to REAPER real quick. And let me enable some recording for my voice, and let's put on the track an oscilloscope. So this is the time domain representation, the thing that was on the left. And then let's put a frequency analyzer on the right. So there you have it. Now the screen kind of looks the same as the other images we had before. So here you can see the sound waves as they're being picked up by the microphone, and this is a representation of of the frequencies that my voice is making. And I guess because we are implementing this transformation going from left to right, I think that maybe a good goal is to draw one of these diagrams, one of these frequency spectrum analyzer things. So that's going to be our goal. As I said, you can go from right to left. You can also go from left to right or back. And in this case, these figures here are just showing the cosine and sine waves that make up the signal. So you can think of like a frequency of 500, for instance, on this line in the graph. This frequency is represented by a cosine wave and a sine wave that cycle 500 times a second. So there would be like maybe say that this one is cycling 500 times a second. And then when we are doing this decomposition, going from the time domain to the frequency domain, the way that this works conceptually, I mean, it sounds like magic, right? How can you get a signal in the time domain and find all the frequencies that are in there? It's kind of like magic. And this is something that is not necessarily in the book, but I picked this up from watching some other videos about the Fourier Transform. So the principle behind the Fourier Transform goes like this. Suppose that you are like in, maybe you are in a room and there is a guitar, and if you sing the note that is one of the strings on the guitar, the string on the guitar is going to resonate and is going to vibrate along with your singing. Just if you have the right frequencies. If you sing in some other frequency, it's not going to resonate. It's not going to vibrate along with your voice. The principle behind the Fourier Transform is kind of similar. What we are going to do is for each one of these waves, so for each one of these components, one of the frequencies in the signal, we are going to check how much of this frequency exists on this signal. How much of this frequency exists on this signal? How much of this frequency exists on this signal? So you can think of this as like the strings on a guitar, except that we have more strings, so maybe a harp. But we are just going to look at, we're going to like play the sound in the room, and we are going to measure how much the strings vibrated. And then with that, we can determine how much of a certain frequency exists in the original signal. That's the principle behind how the Fourier Transform works. But then the question becomes, how do I measure how much the string vibrated? I mean, I guess you could have, in this real world analogy that I'm making, maybe you could have some sort of pickup that would pick up the vibrations. but in this case we are working with samples and mathematics. So how can we do that? Well, there is this concept called correlation, which is how much a signal is similar to another. And the similarity is just if you notice any resemblance in the two. And just by looking at the pictures, I don't think there is really any resemblance at all. But mathematically, we can define this correlation as you take each one of the samples, you multiply by the other sample, and then you take the second sample, multiply by the second sample, take the third sample, multiply by the third sample, and so forth. And then you add up all the results of the multiplications. This is going to give you a measurement of the correlation between the two waves. Think about the things that could happen. So if your amplitude is 1 and the other amplitude is -1, the multiplication of this is going to be -1, right? 1 times -1 is -1. And that's a very negative number. It means that the signals are not correlated. Suppose that you have a 1 and a 1 here. 1 times 1 is 1, so that is a very high number. If you think about the range between -1 and 1, 1 is a very high number. It's the highest number. A positive number means there is a lot of correlation between the signals. And then you just keep doing that. Sometimes the signals may be correlated in some parts, but not in other parts. So maybe in the beginning here, we have more high frequency energy because there is a big jump, but then later there is more lower frequency energy. So maybe in the beginning, this sample here is going to correlate better with this one, but then over there, it may correlate better with this one maybe. And because you're adding up all the products from all the samples, you end up with a single number. That single number means how much this signal is correlated with this one. And then you just keep doing that for all the cosine waves and the sine waves, and you end up with the result of the Fourier transform. Now, the result of the Fourier transform is not given in terms of amplitude. If you look at this graph is plotting frequencies and amplitudes. And the Fourier transform is not going to give us a result in that domain. It's not going to give us amplitude. What it's going to give us is this so-called real parts and imaginary parts. And if you know about imaginary numbers, then that's what this is about, but you don't have to think about it that way. You just think about cosine waves and sine waves. Cosines are called real numbers, sine waves are called imaginary numbers. Just go along with that. And then there is another thing that you have to do, which is to transform these real and imaginary numbers into amplitude and phase as well. In fact, we here are not plotting the phase, but we can. So this purple thing is the phase of the signal. So if you decompose a signal in the time domain into the frequency domain, you get two parts, the cosine wave and the sine wave. These two parts together can recreate the original signal. And from the cosine waves and the sine waves, the so-called real and imaginary parts, you can come up with a magnitude and phase representation of the same signal. So let's write this down so it becomes clearer, hopefully. So there's the time domain. And then from the time domain, you can use the discrete Fourier transform to get to the frequency domain in terms of real and imaginary parts, where the real is the cosine and the imaginary is the sine. And then you have to do this other transformation that will also get you numbers in the frequency domain, but it will be represented in terms of magnitude and phase. And you cannot throw away one of these parts, okay? You cannot throw away the real or the imaginary or the magnitude or the phase. You have to have both the magnitude and the phase to be able to recreate both the real and imaginary, to be able to recreate the original signal in the time domain. That's the game we are playing. And all of these transformations also go the way back. So if you have some magnitude and phase, you can recreate real and imaginary and then recreate the original signal. So you don't lose any information. It's just a different way of looking at the same signal. And some things are, for instance, to actually make sense of the frequency or even to make sense of the phase. Of course, it makes more sense to do this in the frequency domain. Looking at this wave, it's very hard to find what is the frequency of my voice, but looking at this becomes slightly clearer, though this is very bumpy, so I guess I am going to like increase this and integrate. Maybe not so much, maybe something like that. Maybe something like this. Maybe this is a better representation. So you can see that the energy of my voice is around 100 Hertz. And this kind of visualization helps you understand that, while this is not easy to parse. You cannot just look at this wave and say that it is at 100 Hertz. Right, okay, so this is what we are trying to do today. Let's follow along with the book, and we are going to skip some parts that we don't care about, like there is this whole discussion about continuous waves. We are working on the discrete domain, so let's not worry about that. And then, so there is this discussion of going from the time domain to the frequency domain, getting a real and imaginary parts. And then in the book, they actually talk about the inverse first. They talk about how to go from the right to the left. But because we are interested in like drawing a frequency domain spectrum situation, let's go with the forward DFT first. So let's skip this part about the basis functions, and then synthesis, calculating the inverse DFT, let's skip that. And let's go to analysis, calculating the DFT. So going from the time domain to the frequency domain. And by the way, there is actually this interesting discussion here. Back when this book was written, this is not a recent book. Back when this book was written, they say that you would use the thing that we are about to implement if you have interest in 32 or fewer points. So if you have interest in just 32 of these bumps, you are dividing the spectrum in 32 bins, then it may be actually faster to do it with this way that we are about to implement, but typically you would use FFTs. In fact, using just 32 points is not granular enough. I don't think that there is even this option here on this implementation. Oh, there is. So let's see. They say that if you are going to use 32 points or fewer, then a DFT, the thing that we are going to implement, may be faster. Otherwise, you go with the FFT. And in case you are wondering, the relationship between DFT and FFT is just the implementation. They are going to compute exactly the same numbers, but the FFT is generally faster, given that you are using more than 32 points. Otherwise, you would use the DFT. Maybe that's not the case anymore. I don't know. But in most situations, you wouldn't want 32 anyway, because look at this. There is very little information in this graph. So, and that's because there are only 32 of these points here, so we can actually see the points moving around. Right, okay, so we are going to implement something that is probably never useful, but it may show how the technique works. And then we may implement the FFT as well, just for fun, though it comes with JSFX, but it would be nice to implement it from scratch to see how it works. And it's not too much code anyway. So let's skip to the part where there is these equations, and these are the equations we need to implement. So Bo says, in my head, it seems weird that the imaginary number sign starts at 0, whereas the real number starts off 0. Okay, so let's talk about this, which is a subtle point, but it's a very important one. So as Bo pointed out, both the cosine and the sine waves, they start as a straight line. You can think of this as sine and cosine waves of a frequency of 0. There is no cycle. They don't oscillate. And this is just the number 1 over and over. And this is just the number 0 over and over. Right? There is no oscillation, so it just starts there and it stays there. And that's because the sine of 0 is 0, and the cosine of 0 is 1. So if there is no oscillation, it just starts at where they start, and they stay that way forever. Now, why is this important? Well, because the cosine wave at a frequency of 0 is something that has a special name. We call this a DC offset. If your sound wave is not averaging here in the middle, it's not averaging around 0, then how are you going to decompose this signal? So let me show you what I mean. I have this DC offset effect that I can throw here. And when I do that, I can move. So the implementation of this effect is trivial. All I do is just take the sample and add an offset to the sample. So I'm just literally adding a number to each sample. But when I do this, you can see that now it's not averaging around 0 anymore. And in this representation, it's actually highlighting the portion between 0 and my sound wave. But you can see that it's not averaging around 0. So how would you represent this signal using cosines and sines? Well, you use a cosine of frequency 0 and you multiply by, I guess, 0.53 in my case. And then that's how you represent this wave. And in the frequency domain, usually the spectrum analyzers don't deal well with a DC offset. It just shows up as this like huge bump in the beginning. Yeah, now that's more like it. Minus 60 is like my noise floor. Yeah, and it bumps all of this. So it may seem like there is a lot of energy around all these frequencies, but that's not true. That's just a DC offset that is like throwing everything off. This is more realistic. There is just a bunch of energy around 100 hertz because, as we noticed before, there is a lot of energy around 100 hertz. But in my case, because I'm now using an FFT of size 32, this is the size of the bin. So all of this gets conflated into a single bin, a huge bin around, I guess, until 1 kilohertz. Okay, so that is the story of the cosine wave of frequency 0. Then there is the sine wave of frequency 0. That's just at 0 at all points. So you can multiply this by any number you want. You're still just going to get a bunch of zeros. In fact, there are some representations of the results of a DFT that omit this number. They just skip this number because it's guaranteed to be 0. There is necessarily 0 energy here because there is no oscillation and there isn't even a stationary component to this. So it just stays at 0. And the same is true of the sine wave at half of the sampling frequency. Okay, so I didn't actually exactly talk about this, but using discrete signals, you can only represent so much. And there is this theorem called the Shannon-Nyquist theorem, and it says that if you have a sampling rate of, for instance, 48,000 hertz, as is my case here, I can only represent frequencies up to 24 kilohertz. So in this case, the sine wave at frequency 0 and the sine wave at frequency 24 kilohertz, they are both always 0. And that's just the way that the thing works when you just calculate how the oscillation is going to work. If you have a cosine of half the sampling frequency, it goes down and up and down and up like that. But the sine wave would go up and down, but you are only catching the sine wave when it's crossing zeros. So you end up with, so if you had a continuous signal, which is not the case, but if you had a continuous signal, it would go up and down and up and down, just like my cursor is. But my sampling just happens to catch the wave exactly at 0. So we end up with a bunch of zeros. So again, similar to this one, many FFT implementations are just going to skip this output. So you have to be careful about how you are going to use the output of the FFT because it's going to be skipping a couple values. Right. Let me catch up with what you all are saying, and then we are going to start implementing the equation 8.4. So Aaron is here. Hey, Aaron. Great to have you here. And this is something called the Euler Formula, which is a correspondence between exponentials with imaginary numbers and trigonometric functions. So the real part of this and the imaginary part of that, yes, that's where the names come from. It arises from a Taylor series expansion of exponentials, cosine and cosine. Yes, in fact, if you are implementing on a computer the cosine function, usually we just take it for granted. It comes with JS effects, comes with many calculators, but if you didn't have that and you had to calculate the sign of a number given just multiplication, addition, and so forth, one way is to use the Taylor series. I'm not sure if that's how calculators actually do this, but I know it's one way of doing it. And that's where the names come from. That's why cosine is associated with real and sine is associated with imaginary numbers. And that's something that we touched on in a previous stream. Trigonometric functions. When we were talking about hyperbolic functions, I mentioned that usually sine and cosine are associated with trigonometry, so they're associated with calculating the relationship between sides of a triangle. But another way of thinking about it is as a plane with a circle, and this is the real axis, and this is the imaginary axis, and then you can plot on this space imaginary numbers, and you can reason about this circle, and sines and cosines play out in this space as well. And the hyperbolic functions work just the same, except that instead of a circle, it is a hyperbole. Right, so that's the story behind the association between real and imaginary and blah, blah, blah. Oh, thank you, Aaron. That's very nice of you. Right, so that's the story. Resonating frequencies, we are going to play the sound in the room, and we are going to look at our harp with many strings, and we are going to measure how much they resonate using this idea of multiplying a sample by the string. So this is one of the strings. It is going to be one of the strings that is longer, so lower frequency, or shorter, so higher frequency. So we're going to multiply a sample by the string, and that is going to give us a measurement of the correlation, and then we add up all the results, and that is going to be our real signal, which is a measurement of the correlation between the original signal and the cosine. And then we're going to do the same for this sine. And we need to put a minus here so that all the equations make sense. And some authors even skip that. Yeah, if someone asks what you're doing, say with confidence, I'm correlating the input signal with the basis function. The basis function is just one of the strings, one of the things that you want to be the fundamentals. In fact, you can expand this idea of a Fourier transform to other functions beside cosine and sine. I think that the cosine and sine are by far the most useful representation, but you could come up with other sets of functions, and you could decompose the original signal into these sets of fundamental frequencies, or the set, not frequencies anymore, but this set of functions. You could decompose the signal into these functions and do something with that. I don't know any examples or applications, but it's just something you can do. And there are some restrictions on the kinds of functions that would make up this, and that would work. I mean, they have to be orthogonal and linearly independent, but never mind that. We're only going to work with cosine and sine. Bo says, I got some of that, need to look further into it. yeah, it's, I mean, reading the chapter helps, and we are going to implement this, so maybe it will make more sense. Right, let's actually write this down. So here on the right, there are my formulas, and then on the left, there is my JSFX implementation. So I'm going to implement a function called, well, I'm tempted to call this the DFT. Usually I shy away from acronyms, but in this case, I think it is it's like RMS, such a pervasive acronym that I think it's fine. So you need to provide me the signal, or maybe the data. I guess I'm using data elsewhere. So I'm going to use data here. Oh, actually, you know what? So this is something that I actually didn't mention explicitly, but it kind of makes sense if you think about it. I cannot calculate the DFT of a single sample. I need to collect a bunch of samples, maybe 16 like in this case, maybe 32. I need to collect a bunch of samples, and then I'm going to calculate the DFT of that collection of samples. The number of samples that I collect determines the number of bins that I will end up with. So in this case, I have 16 samples, so I have 9. That doesn't really make sense. Oh, it does make sense. Yes, right. So what happens is I have 16 samples to begin with, so I will end up with 18 samples because both the sine and cosine have one extra at the end. But then you can also get rid of these two, so you end up with just 16. And then you didn't lose any information along the way. You also didn't create any redundant information along the way. In any case, the point I'm trying to make here is if you shift this around, I was going to say that it doesn't affect the amplitude, and that is right. It does not affect the amplitude, but it does affect the phase. So I guess I'm going to use a circular buffer. So the discussion I had in my head was whether I should have just a block of memory, or whether I should have a circular buffer. The difference being a circular buffer has a notion of where I'm at, and yeah, I do want to have that notion because I want the thing to be, I want to calculate the phase correctly. Right, okay, so never mind that. I'm gonna go with data, which is a circular buffer, and I may not need anything else because a circular buffer comes with its size. Oh, maybe I need some space to write my answers into. So I guess we are going to implement one of those functions that is kind of weird in the sense that it receives as argument not an input, but an output. So I'll call this the real part and the imaginary part. I could call this cosine and sine as well, but let's try to recreate this formula here. Oh, in fact, if we are doing that, then we probably want to use some x's and k's and these kinds of names, but we'll get there. Right, so the data is going to be a circular buffer, and we need to traverse that circular buffer. We will have a variable called I, and I is going to range from 0 to the number of samples minus 1. So let's try to first get a hold of this capital N. Capital N represents the number of samples in the data. So my data is a circular buffer. From the circular buffer, we can extract the signal, and then from the array, that is the signal, we can extract its size. Conveniently, there was another use of this right below. So we'll call this the N. That's the number of samples that we are given, something like 16 or 32. Then I am going to have a loop, right? So I need to have a loop. Actually, I need to have two loops. I need to have a loop, one loop per bin, and then I need to have another loop on each one of the bins. I need to loop over each one of the samples. Right. Okay, so let's do this. I will have a variable called k, and I am going to start with k equals -1, and then I will loop over n divided by 2. Okay, so it's saying here the index blah runs from 0 to n-1, while the index k runs from 0 to n divided by 2. But that's inclusive. So it goes from 0 to n divided by 2, which means that it runs for n divided by 2 plus 1, this plus 1 being the 0. And then I will do that bit. And then I'm going to do exactly the same for I. So I need another variable called I, and this one is going to go from 0 to n-1. But again, it goes up to n-1 inclusive, starting at 0, so it runs for n times. And I think I'm actually going to leave it like this. I think it actually is more readable if you leave it like this, though it is kind of silly to say -1 plus 1. But it matches the formula. In fact, I think it's better if I just put a reference to what I'm doing over there for people who want to follow along with the code later. Then, I'm going to do some stuff in this loop. I'm going to do this summation in the loop. So let me have a variable called sum. Of course, it starts with 0. And then I will add. I need to get a hold of the signal in this position. So I'll use the circular buffer get from data position -I. Then, so this is going to start at the most recent. I'm thinking if this isn't reversed. Well, I'm just adding stuff, so it doesn't really matter if I'm getting this reversed, right? And then, this is xi. So maybe I'll have a variable called xi. There you go. And then I need to compute this cosine. But I think I have everything I need in there. Right, so let's just write this. Xi times the cosine of 2 times pi times k times I divided by n. Right, k is coming from here, I is coming from here, n is coming from there. So I did all the summation. At the end of this loop, my sum needs to be assigned somewhere. It needs to be assigned to the real part. So I guess I'm going to use... What am I going to use to represent the real and imaginary parts? The data, I think I'm going to use a circular buffer. But the real and imaginary parts, I may use something else. I may use an array. But hang in there, I will want to graph this later, and this is expecting a circular buffer. So I think I'm just... No, but on a circular buffer, I cannot push things so easily. Does it matter? Yeah, I think I'm going to use arrays for real and imaginary. I may use arrays for data as well. We may revisit this. Right, so array set at position k real. Is this a function? Do I remember correctly? No, this is not a function. I think I remember what I did with arrays. Let's go up and find the implementation for arrays. I'll make this bigger and move it sideways so it's not right behind my face. Yeah, in arrays, you have to just get a hold of the data directly. Yeah, I think I will have a variable called rex. Rex is equal to the real part, just the data part of the real part. Similarly for the imaginary x. Just like that. And then I set it like this. I just go to the real part at k equals the sum. That looks good to me. Now let's take advantage of this loop and also calculate the imaginary. So I'll call this the sum real. And I will also have a sum imaginary. And of course, I will change this from cosine to sine. And I think I am just going to subtract instead of add. That amounts to the same, right? But maybe it doesn't look the same on the page. So I guess I'll do it like this. It doesn't really matter all that much. I'm just like changing a signal here, but yeah, I'll do the summation with plus, and then I will negate everything with a minus. Right. So unless I made some mistake, this is, I think, a good first sketch. There are plenty of things we can improve on this, but this is a good first sketch. Let's actually try this out with some numbers. But what numbers? What data do we want to play with? I have an idea. Let's start with something small and simple. I don't know why I'm moving this PDF around, as I'm just thinking and moving it around. Right, so let's start with a sine wave in a particular frequency that we know of, and then we know what to expect from the outputs. Right? We should know what to expect from the outputs. Let me go to my demonstration effect. And on my so there is no data structure here besides the data that I need to provide to the Fourier transform. And I think I already have a notion of samples. Yeah, let me create another page actually. So now this is going to go from 0 to 4, and we'll have this Discrete. See, I learned how to spell it. Fourier Transform. That's page number 4. And if I am in page number 4, if I am on this page, on the sample block, I will want to collect material into that. And I'm gonna do something similar to RMS. I'm just going to compute this on the left-hand side. Let's keep things simple for now. I guess I'm going to create a circular buffer here. DFT samples is a circular buffer new of a certain size. Now, I said that to be faster, it would be probably below 32 samples, but 32 samples does not give me a graph that I like. So let me go up to maybe this. This is a graph that looks okay. So let's do 2048. And then over there, I am going to push into the circular buffer the left-hand side sample. Right, what is next? Well, when I am on that page, on the GFX block, I will need to compute the DFT. Now, I could compute the DFT over here, but that's a very slow operation, and I'm not going to show stuff as often as I calculate stuff, right? The sample block runs 48,000 times a second, the GFX block around 30 times. So it's much better for me to calculate the DFT over there. And that's what I'm gonna do. So I need to also instantiate this real and imaginary stuff. I will have a DFT real, which is an array of this size. I need to divide by 2 and add 1. Remember that so remember that this is, oh no, not that. This, so if we had 16 samples, the real part would have 9 samples. 9 is 16 divided by 2 plus 1. Got it. Alrighty. And the same for the imaginary part. LD drums 20. Hey LD drums 20. Great to have you here. And you are asking STFT right. STFT short time Fourier transform. What's that about? I'll answer a question to the best of my knowledge. I have no idea. I don't know. Maybe. So maybe this STFT is a particular case of the discrete Fourier transform for continuous signals like this. And I know that there is more we need to do, okay? There's like this windowing function, and there is a lot more. All right, it's doing FFT over time. Excellent. So that's what we're doing. Maybe I should call it STFT. I don't know. But I'm doing it over time, and there is more stuff we need to do, like windowing and whatnot, but I'm not going to get into that today. Definitely not today. Right, so I have my real and imaginary parts to pass along. Let me grab those and put them here, and DFT samples as well. And then let's just compute the DFT, just like that. So now the real and imaginary parts have been updated. Oh, but I'm doing this to actual samples, right? As they come in, that's what I'm doing here. So these are going to be crazy numbers, aren't they? And I believe there's some stuff that I also need to do, which is to divide by the number of samples to make this usable. So let me find some equations to just verify this. I think this is called like normalizing this. Yeah, I think that at the end we need to divide by the total the sum of all the elements in here to normalize this so that it adds up to 1. But couldn't find it, so I'm not doing that right now. And I am thinking this because I think that the range of these numbers is going to be way above 1. Let's in fact debug by finding the real part, which is an array, so I can get the data from the array at position 0 and look at that. So let me drop a demonstration effect into the track as the first one, why not? I'm going to go to the Discrete Fourier Transform page, which is making everything a lot slower already, so that's probably progress. Let's look at debug. Now this number is reasonable. It is going above when I speak, but not too much. Right, so I guess it is safe for us to plot this guy. Is this stream okay? Is this affecting the quality of this stream? Because I'm doing some crazy stuff in Reaper. Let's plot this. Oh, to plot this, I need a circular buffer. I only have a function that plots a circular buffer. That's kind of annoying. Let me catch up with what you are saying and then I'll think about it. You want to get familiar with that to perfect reconstruction, overlap, add, and so on and so, yeah. Okay, so yeah, there are many things that we need to talk about. Windowing, overlap, add, lots of stuff. It's not so simple. And I'm just doing visualization right now, but I want this to be able to work with processing audio on the frequency domain. So, well, actually for this function, I don't have a lot of ambition because I know that it will be terribly slow. I mean, there are so many ways to optimize this. For instance, I'm recalculating this term over and over. But check this out. There is nothing about the signal in here. K is given by the number of samples. I is given by the number of samples. N is definitely given by the number of samples. It is the number of samples. So you should pre-compute the cosine and sine and store them in arrays so you don't just keep recomputing everything over and over. So many low-hanging fruits. Yeah, so the short time Fourier transform is the way to go. Fair, correct, and we'll get there at some point, but not right now. Let's finish by doing, maybe we will not be able to actually plot anything and see anything, but let's do also this computation to transform this into magnitude and phase, so we are closer to this. Now, the equations that we are interested in are these equations. They go from real and imaginary to magnitude and phase. So let's implement this idea. Bo says phone. LD Drum says, you are doing everything by hand. Mad respect. Okay, Bo, what do you mean by phone? And LD Drums 20. Yeah, I'm doing everything by hand because I want to learn how it works. And then we will be able to like compare our implementation to the Reaper implementation and we should get exactly the same values. It should be fun. And I think we're going to even implement FFTs as well. I mean, DFTs, this way of computing the DFT is 10 lines of code. It's very straightforward, but it's super, super slow. I think we will implement FFTs as well because they're fun. And then when we learn everything and we know how to use everything, we are going to use the REAPER functions to make things fast. Right, so I am thinking that maybe I don't want to put this function in the DFT namespace. I'll go with that for now, but maybe this, because this is not really about the DFT, it's more about the representation of real and imaginary numbers into magnitude and phase. And we may have something that is like a library for some library functions to work with imaginary numbers. Yeah, I'll give this the imaginary namespace, and I will go up and I will do this near the mathematical functions and the unit conversions. Maybe I'll do this below mathematical functions. Or actually, I'm going to rename this to hyperbolic functions. And I will put this, it doesn't really matter, I'll just put it here. There you go. Rectangular to polar. And I think I'm going to implement first just the formula for one number, because you can see that this is ranging over k numbers. But I could just do it for one number and then loop. So I'm going to do this for one number. I'm going to call this, maybe I will have a data structure to represent imaginary numbers with real and imaginary parts, but I'm just going to start simple. We're having a real part and an imaginary part laid out here, instead of having a data structure for that. Yeah, because we have to allocate memory in the init block, I think it actually makes more sense to do it like this. Otherwise, you would have to allocate a lot of variables just to pass them around. Same story with X and Y positions on the graphical part of the interface or of the library and JS effects in general. You'll see X and Y, width and height. And I could group them in a coordinate data structure, but I don't think the ergonomics of that are very nice. So right there you go, real part and imaginary part. All I gotta do is, well, I will need to compute the magnitude and the phase. So maybe I'll have just a magnitude function. So the same way that we are going to have to loop to compute over the array, we'll also have to call magnitude and phase. And that's just because it's annoying to return two values from the function. So magnitude is a square root. That's what, I don't know why they used this notation, but maybe because it kind of matches this notation well. But yeah, the half here is just taking the square root. So the square root of the square of the real part and the square of the imaginary part. And then another called the phase. Again, I will have the real part and the imaginary part. And it kind of becomes annoying that the real and imaginary here are numbers, while the real over there in the DFT is an array. We'll have to revisit those names. Right, so the imaginary phase is this. And there is a whole section of this chapter talking about how this computation is actually not so simple. We already have arc10 of a certain number, so we could do just this. Right, and arc10 is, I think it's spelled like this. It comes with JS effects. Come on, get me there. Oh, please, yes, there you go. So arc10, it's just A10, okay. And this is something that comes with REAPER, so I could just do this, but there are actually this is not so simple. There is a whole section of this chapter talking about how this computation is not so simple, because this is going to give you an angle, but the angle of 0 is equal to 360, right? So there is a lot of ambiguity in the result of this function, and there is a lot of things you have to think about, like if this number is negative and the other one is positive and blah, blah, blah. And I think there is like, the section is called nuisances of the polar representation. Yeah, polar nuisances. And you have to think about all of this. You have to think about what if the real part is 0, then you don't want to divide by 0, and blah, blah, blah. But REAPER is so helpful. It comes with a function called atem2, and it returns the tangent of x divided by y. So I can do this, and this implements all the small annoying cases from the polar nuisances section. As far as I can tell, I tested this when I was reading the book, and I think it does everything correctly. I haven't really absolutely checked this, but yeah, all right. And I guess it could be fun to go into that chapter or that section and actually figure out all the edge cases and re-implement the tangent, the arc tangent ourselves, the same way that we are implementing the FFT ourselves. But I'm not going to do that right now. I'm just going to do this. And then what we still have left to do is to loop over the k numbers to get the magnitude and phase. So let me split the screen this way and maybe move the window there. And I will write a function to do just what I described. So it's called DFT. So this time, I think it makes more sense to have this as a function on the DFT. Well, maybe not quite, actually. Maybe it still makes more sense to have this loop over here with the imaginary number functions. I'll have a function called imaginary rectangular to polar. And in case you're wondering what is this rectangular and polar all about, if you have a real and imaginary number, that's called a rectangular representation. Coming back to that figure on Wikipedia. Yes, so if you have the coordinates of this in terms of x and y, this is called the rectangular coordinate because of, well, you can draw a rectangle here. And if you have instead a magnitude and phase, the magnitude is how far away this point is from the origin, and the phase is the angle. And if you have these coordinates, it's called a polar coordinate instead. LD Drums 20 says, seeing your CV, you're quite an educated dude. Makes sense. Most people would just stick to the libraries and call it a day. Thanks for sharing this. Well, I want to learn about the libraries, and I'm developing my own library. Isn't that fun? And yeah, I am somewhat educated. I have been around. I have been in schools. And I know that in some ways, like in terms of usefulness, I think that this is not super useful. There are libraries that implement this already. There is Cook DSP, for instance. There are libraries that implement all of these things and more. But we are learning about this. Right, okay, so rectangular to polar, I need to get my real and imaginary and my magnitudes and phases. Well, I'm not calling it reals, I'm calling it real. I guess I'll call this... No, yeah, there you go. I was saying that here the real and imaginary were numbers, and below they were arrays. that's how we are going to fix this. Phases. There you go. And how about I go there to the DFT stuff and change that as well. So instead of real, in these positions, I will have reals. And instead of imaginaries. Right. Then I need my n and my k. My n is going to be... So another thing that I could do, but I'm not going to, is to check that all these guys have the same size. They should have exactly the same size. I'm not going to do that because checking for these kinds of things makes everything slower. And we are already very slow the way that we are. So that's what this is about. I'll just grab the size of the reals and suppose that you are smart enough to call this function with all of these arguments having the same size. Then let's do a loop that is going to look a lot like this. Except that we are going to go up to n minus 1. So we are going to loop n times. And let's look at the formula to see if that's how they are notating that. They are saying to go from 0 to n minus 1. That's what we are doing there as well. Great. Oh, but this is the wrong formula. This is not the formula to compute the polar stuff. Yeah, they don't even talk about the range here. They just give the equation and you're supposed to think about the range yourself. That's fine. We are just going to go from 0 up to n. And then what we are going to do is, well, we need to fetch these guys again. We'll also need to fetch, so this needs to be local variables, re(x) and imaginary x, and mag x, and phase x. The capital X means we are in the frequency domain, while lowercase x's like those in Formula 8.4, these lowercase x's mean signal in the time domain. Where's my equation? I lost my equation. Oh no, where is my equation? There you go. I don't really need it. I already implemented, but whatever. So let's see. My mag x and my phase x, magnitudes and phases. So then my mag x at k is equal to this. And then for the imaginary, not the for the imaginary, for the phase x, I will do phase of the same values. And that concludes the thing. It actually loops over. And I remember saying that I had to do something else when I was looping over. I forget what it was. Whatever. This should do it, but... Oh, maybe the normalization thing. I'm pretty sure I need to normalize this. In the JSFX documentation where they talk about FFTs, I think that they have something about this. Yes, you have to scale this down, dividing by the size. I don't know when I'm going to divide by the size. I haven't decided, but I don't care. So maybe we can try to plot this real quick, and if we are wrong about this size thing, it's just gonna be super big, and then we can scale it down if necessary. So right now we are computing the DFT and we are getting a hold of the imaginary stuff, and then let's call this other function to do the polar. With our real and imaginary, as well as two new arrays that we have to define. They are going to be not the real and imaginary, but the magnitudes and phases. And they have to have the same size, right? As the real and imaginary. So and then we need to plot this, but they are not circular buffers. What can I do to actually plot this real quick? I am going to copy and paste some code. It's not ideal, but it will plot something, hopefully, maybe, and we'll see what it plots. I'll just grab this code that is doing the line graph. I'm going to paste it there, and we are going to hack this together, and we are going to wrap it up. So in terms of data size, this is going to be based on the samples. No, the real part. The real part is not a circular buffer. It is already an array. Then the data point width, I need to give this width a value. So I'll say that the width is gfx width. And if I have width, I bet that I have height as well. gfx height. I'll put them there. This and that is covered. Then that is okay. And then this data, I am going to get the data from the imaginary part. Now that is an array, right? So I'll say array struct data. Why am I doing it on the imaginary part? Let's do this on the magnitudes. That's the data that I'm going to plot. And then how do I get the data? I do it like this. The data size is correct. Oh, how about I get it from the magnitudes? So now it looks kind of nice. Then all this line situation seems right to me. And then we also need a thickness. I'll do a thickness of like 3. I'll move this up. We'll also need X and Y. I'll move this up as well. I'm moving these around, not that it matters that much, it's just that now it kind of resembles the function call, except that I inlined the function and I modified it so that it now works over arrays. So data, data size, x, y, width, height, and thickness. These are the arguments to call that function. Then this is just the body of the function adapted to work with this, except that when we are looping, we need to change this circular buffer stuff into some index stuff. And I think that is it. Now, what are the chances that this is gonna work? very small. Let's try it out. Square root needs one parameter. That's not what I meant. I meant to say plus. Okay, at least it compiled. And then discrete Fourier transform. There is a line there, but it is a bunch of zeros. Alrighty. Looking at VS Code extensions, there is one that provides IntelliSense for Gsonic effects. It has advanced quite a lot since the last time I fiddled with it. REAPER script, I don't know. Which extension is that? And Aaron says, need to head out. Great work. We'll catch the rest of recording later. Great. Thanks for doing that. Thank you all for being here. What we're going to do tomorrow over here on my channel, same time, 6:30 UTC, is we have a song. We have been recording the song. Aria from IDDQD Sound is going to be here. We are going to mix, maybe do some editing. Oh, second one, you say? Oh, so this is not just for REAPER scripts. I looked at the name and I was like, okay, this is for Lua. Are you sure that this supports JS effects? Doesn't seem like it. Everything in here seems to be about Lua. Oh, but there you go. It does support JS effects. Nice, I didn't know that. I'm not like jumping up and down because the language is so small and the syntax is so simple that syntax highlighting will not help me much probably, and IntelliSense is not something that would help me too much unless it does IntelliSense based on the functions that I defined. That would be kind of fun. But the JS effects functions are just like FFT, so straightforward. Yeah, all right. Anyway, thank you all for being here. Thanks for participating on the chat and for going to Patreon and PayPal and supporting my work. And tomorrow we'll be doing that mixing and editing of the song. And on Thursday, we may do this follow-up to what we are doing now. We may do something on IDDQD Sound's channel. We'll see. All right. I catch you all tomorrow over here. Bye.